echo. So YouTube takes a second. Incredible. I can hear the echo, which means we're live on YouTube. Hey, everybody. Thanks to the people who are in the Zoom call. Thank you, everyone, for joining the YouTube live stream as well. This is my first time hosting the paper reading group. I've been doing a few community things for weights and biases for a bit, but I'm excited to host my first paper reading group. And I was chatting to a few people in the Zoom call. It's their first paper reading group as well, which means I'm allowed to mess up since they don't have a higher bar from earlier from my colleagues who've been hosting this. Awesome. Let's get started. Let me share my screen and tell everyone what I'm planning to cover. So my agenda for today is to cover the classic. It's classic because it came out in 2015 and has been quite influential. Don't at me for it. But I want to cover the unit CNNs for biomedical image segmentation paper that came out in 2015. At Weights and Biases, we've been hosting the paper reading group for quite a time. And our sole goal with this series is basically to empower you to be able to read papers, to be able to implement papers, which is, as I'm sure everyone would have come to understand, a core part of all of our jobs working in machine learning or data science. This is one of the image segmentation papers, one of the classic image segmentation papers that quite revolutionized this architecture called UNIT, which has affected since then a lot of things. And here are the resources that I have studied basically, and I'll be stealing some stuff from, I'll be giving credit, of course, to cover the UNIT paper. My goal today is to cover the paper, give you enough context to, first of all, if you need a recap on CNNs and all of the architectural details, we'll quickly glance through that. Then we'll try to read the paper today and cover its implementation in Pytorch. After that, I'll try to cover a few Kaggle competitions, or at least leave you with some homework to work on from here. Let me make sure everyone's muted in the Zoom call. Awesome. So one quick note to everyone on the YouTube live stream and in the Zoom chat, if you could head over to this link. I'm sorry, I should stop sharing my screen. 1 second. So if you'll head over to this link, it should take you to our community where you can sign up and ask questions. I have one request. If you all could please keep the discussion on here instead of the YouTube chat and the Zoom chat. Since it's two different locations, it's a little difficult for me to keep an eye out. If you're new to Discourse, it's a straightforward interface. If you want to ask any questions, you can simply ask them here. And other folks can like your post or reply to it. So please post the questions and discussions here. So I first of all want to start with the question that I've literally posted on here. When do we use segmentation? And just to recap what exactly segmentation is, if anyone in the Zoom call would like to unmute themselves, or if anyone would like to help me out here, the question is, what is image segmentation and why is it useful?
Well, I can go. Image segmentation is basically the target being that given an image without any depth information, is there a possibility that we can sort of group out objects that we feel that we know because we are humans and we sort of understand what objects are and we sort of have much more information. But can we do the same thing based on images, just images that we can group out or segment out parts of the image that relate to the same thing?
That's a great answer. Thanks for that, Saurabh. When you say depth, could you elaborate on what do you mean by depth?
Depth as in, an image would get you 2D information. That is, all of those, the thing that you view, if it's from a single camera perspective, you basically end up with a 2D image where this person here that has been segmented as blue, and this tree here that is in green, to a computer, both of these are in the same sort of space, because it does not know that the tree is sort of behind the person, so to speak. And there are ways to, I think, infer depth using depth sensors. I think infrared is one of those sensors, but I might be wrong. Uh, but there are other depth sensors, and we sort of can get depth information to get better segmentation, but that is what I mean by depth. Sorry.
Thanks, Saurabh. That's a spot on answer. So just to add to that, there are different categories of image tasks that I usually aim for in papers. Image segmentation is one of them. Sorry. Image classification is the classical hot dog or not hot dog, dogs and cats example. These one that comes from there is localization. So let's say you want to tell what's in an image, like I want to point out where all of the humans are, that will be localization. So I can maybe draw a bounding box. Think YOLO or those papers. If you're not familiar with them, that's totally fine. Just think of the bounding boxes that you see in a lot of animations that are thrown around on Facebook. That is localization. The next step from there is image segmentation. And like Saurabh just pointed out, whenever you want to understand every single pixel inside of an image, and assuming you don't have the depth knowledge, you don't have a depth mapping. And like Saurabh said, with 3D cars, you usually have LiDAR sensors, which are light image and detection, or you could have IR sensors, infrared sensors, which give you depth information. So you, in your arrays stored in memory, could have numbers that would tell you how far away is an image. Like right now, you can sort of tell, because I have a high fidelity camera, that I'm slightly away from the screen and my hand is now closer because it gets larger in size. But to a computer, it's slightly harder to tell those things. So image segmentation is taking every single pixel and putting a label on it. And from there, you can derive different knowledge. So it's also one of the challenging, not the most challenging, but one of the most challenging problems, image tasks. So let's start with some background concepts. I want to give a quick brush up on all of these concepts. If you're familiar with these, I'll keep it short. If you're not familiar with this, I'd love to help you get up to speed. Let me start by talking about what are convolutions, what are max pooling layers, what is a transposed convolution, which was very key to this paper. And I'll quickly touch on what is cropping and data augmentation. Someone asked, where can they ask the questions? Let me post the link real quick. All right, let me stop sharing my screen and share the correct one. By the way, as a reminder to everyone in the Zoom call, please feel free to interrupt me anytime, since you all are in the call literally. Please unmute and interrupt anytime. So I'm going to use this Excel sheet that came out of a fast.ai lecture. It's one of the best deep learning courses in my opinion. And this is on a toy data set, at least in today's world, called MNIST, which has numbers from 0 to 10, 0 to 9, sorry. 10 is 1 and 0. And this is just to demonstrate what a convolution operator is and what a max pool layer is. So here, as all of you can clearly see, this is a number. 7 looks like more of a bird, or the Swift programming language logo. Well, that's the problem with humans. It's a 7 if you look at the label, and that's why problems arise for machine learning models as well. The key thing to remember, all of these numbers that we see, these are black and white numbers, which means it's just one layer, are just arrays stored in a computer's memory, right? So wherever you have some value coming up, some shade coming up, you'd probably have 1.0, which means this is black, or in this case, a red pixel. And wherever it's nothing is written in memory, it has a 0 number on there. So this is our input image, and our task is to maybe able to predict it. Let's not bother about it. For now, we'll take a filter. We'll actually take 2 of them and apply the convolution operator on it, which gives us this output labeled as conv1. Now, how do we get these numbers in the conv1 layer? Let's take a look at this formula. And here's the nice thing about Excel. It tells me exactly what's going on. So what we've done is we've created this filter that operates upon all of these numbers and quite unsurprisingly should give us a zero because it's everything being multiplied by a zero. Let's see, how do we get this 4? So as a result of convolving, that's the term here, this filter over these numbers, we get this output. And we do this set of multiplication over the entire set of input image pixels to get this output. And we do this twice because we have 2 filters. So as you can see, with just one convolution, we've increased the depth. This is a key thing to remember for unit, and a challenge as well that we'll just get around to. From there, you can do more convolutions, which will keep giving you more outputs. Key thing to note here is as you progress inside of this layer, now you have 2 filters being applied on this. This single number has a receptive area of these numbers, which further are derived from, let's say, somewhere around this region. So the key point to remember here is, as you go inside a network, as you go deeper into convolutional neural network, one single pixel, let's say this number, would probably be corresponding to a lot of these. Now, as we'll see later, I'm giving a spoiler here with image segmentation. This is counterintuitive, right? Because if I stop sharing and reshare the correct screen again, what we want for image segmentation is the ability to be able to label every pixel. For that, you need a number for every pixel, a class label. Let's say ground is class 0, and the predictions, right? Now that's hard to do with convolution neural networks as the output shrinks. So we look at how that is tackled, but that's one key thing to remember for now. So this is how we apply convolutions. Another operator I want to give a quick reminder of is max pool. So how do we get this number? That's simple. We take the maximum of these 4. So this is a max pool of 2, which gives us this one output instead of these 4 numbers. The key thing to remember, this is being written in an expanded fashion, but as you can see, this matrix is probably shrunk down a bit from the original one. So as you apply max pooling layers, the output size shrinks a bit. Let me look at another number. So how do we get this 25? We take the maximum of these 4 numbers and just replace this pixel from that. So 25 looks like the maximum here. So we should be getting 25. Yes, we do. That is max pooling layer. I'll probably skip the later details because those aren't important, but I quickly wanted to give a quick reminder on convolutions and max pooling. Any questions about this if anyone is new to it? Awesome. I don't see anything on the forums. I should probably share OneNote at this point. So now I want to cover another concept. I'm covering these topics with the goal in mind to get everyone up to speed with the background concepts required to understand units. So now I want to cover upsampling, which I'm going to derive from a blog post called Upsampling with Transpose Convolution. This is by Naoki. I've also linked this in the forum thread. But upsampling refers to fractionally strided convolutions or deconvolutions as the same thing. Someone's asking where can they find the Excel sheet. If you head over to the forum link that I've shared, I posted the entire resource list there. Please find it there. In case I haven't linked in there, please let me know. Awesome. So coming back to my OneNote. Now we've just looked at convolutional operator, and let's say this input is a 4x4 array on which we apply a 3x3 kernel, and you would maybe get an output of 2x2. Now, the problem here, as I alluded to earlier, is for image segmentation, you need a label for every single pixel. But even if we get an output from this, let's say this is our input, these do not correspond. So the key thing here to understand is we need a way to be able to upsample, upscale this. And for that, let's look at deconvolution. So it's the somewhat opposite of convolutions. And the blog post I've referred to for this actually shows you how it works. I'll just give the gist here to keep it brief. But let's say you have a 3x3 kernel. This can be rearranged into a 4x16 kernel. I'm just literally quoting the example I read in the blog post and just trying to explain it. And what we end up doing here, let's say this is row 1, this is row 2, this is row 3. We put row 1 here, 0 under it, 0 under it. We put row 2 here. Put a 0 here. We put, again, I believe row 2. So we fill the same array expanded into this 4x16 convolutional kernel. We've just taken this kernel and resized it to 4x16 in a way by filling it with zeros. In the blog post, they show you how performing the same convolution again that I referred to earlier with the 4x4 input would give you the same output as just multiplying this layer. So earlier we were taking this 4x4, let's say, image. I mean, it's a small image, but let's work with that. You perform an kernel operator, a convolution on top of it, and you get a 2x2 output, let's say. If you do the math and if you actually check it out, if you take this resized 4x16 kernel that came out of this 3x3 kernel, and if you just resize the original 4x4 input into a 16x1 input, you get an output of 4x1, which can be resized to 2x2. And if you do the math and perform the convolutions and actually check the numbers, they should be the exact same thing. So the point being, resizing the kernel like so doesn't change a lot of things. Now, deconvolutions are also known as transpose convolutions for a reason. So let's say this is a convolutional layer. Actually, it's a kernel, but let's call it C. We can perform a transpose of C and multiply it with, remember the 4x4 layer from earlier? Let's say we take the 2x2 layer, which was coming as an output. So we take the output layer, resized into a column vector. So this would be 4x1. This gives us an output of 16x1, which can be resized to 4x4. So we take the transpose of this kernel, that is just a resize of our original 3x3 kernel. So we take this transpose, multiplied by the output, and we can derive the input. So we've here achieved a way using this operator known as deconvolution or transpose convolution, which allows us to increase the size of the output. By definition, convolutions, which we just looked at the Excel sheet, shrink the size of the output. The key problem there was to work with image segmentation, we need a bigger output or an output that matches with the input image size. So inside of the unit paper, we'll see where this is implemented. We perform deconvolution or transpose convolutions to get a bigger output size. That towards the end will correspond to the input image. Let me take a quick break and see if there are any questions on our forums.
So I'm so sorry, I'm dumb.
Please go for it.
How are we getting that 4x16 thing from? So I get that the 3x3 image is our filter, right? And we are passing an image through. And could you just tell me how are we getting that 4x16 block?
Absolutely, sure. So I am not teaching it myself. I've stolen it from. It's the last link in this list. If you head over to that.
Okay.
Yep. I'll still give a walkthrough. So this was our original 3x3 kernel in their example. I've not taken the numbers because you can run through them and get the idea. But if you just resize them like so, if you rearrange the same 3x3 kernel by putting a bunch of zeros, you can get the 4x16 kernel.
Okay, so this is a predefined kernel mapping, right? It's not.
That is right. Yes.
Okay. And this is specifically being used just for the upsampling process, right? So we want it. Okay. Thank you.
That's correct.
Thank you.
Thanks. Great. Thanks for the great question. Just to point the topic out, it's called upsampling with transpose convolutions by Nauki.
So, excuse me.
Please go for it, Sanjay.
Yeah. So my question is that like the whole purpose of doing the upsampling is to get a 4x4 output, right? So like we can achieve the same thing through same padding as well, right? In the convolution operators. Say if we apply same padding.
Yes. So sorry for not being clear. I'm rushing through things because I just have an hour and I also want to read the paper and implementation. I'll give the complete context. The problem, let me stop sharing to focus on my face. So the problem with convolutions is the output shrinks. And for segmentation, we want an output that corresponds to the input pixels. If we increase this, right? Yes, you could do that. But that wouldn't exactly correspond to the input images. Does that answer your question?
Not exactly. Like, I mean, now usually if we wanted to maintain the size, we usually do padding, right? Zero padding or something. Accordingly, like if you apply same padding, then we can anyway get the like convolution output same as the input size. So like, is there any particular reason why we prefer like the transposed convolution over normal, say applying same padding?
Someone's already mentioned this in the chat, so I'll just use, it doesn't meaningfully expand the tensor. So when you pad it, you lose out on the meaning from the layers. Is that helpful?
Yeah.
Okay. Please feel free to ask on the forums as well if I wasn't too clear, right?
So in a sense, like padding will not upscale the image, right? It will pad stuff to it with random zero values or something, but it will not effectively upscale the image, which we are actually, I think, looking for.
Exactly.
Right. Okay.
There's a lot more detail, I think, in the DC GAN paper where they showed you how to upscale images effectively. But they literally cover this in a lot of depth if you're curious. So the DC GAN paper is the one to look for.
Okay, sure, I will go through.
Thanks. Yeah, sorry about rushing through things, but I try to pack a lot of knowledge because we have folks who are very advanced. I know I've seen some names in the Zoom meeting who probably I think don't need to be in this call, but they're joining us as well, and people who don't know of convolutions might be joining as well. So I'm trying to cover all things here, which is why you might feel I'm rushing through things. If you do, please feel free to interrupt anytime. Awesome. So now we've covered all of the topics that I needed to start reading the paper. And once I figure out where it is in my 50 browser windows, I'll share the screen and get started with reading the paper. So in the next 15 minutes or so, I'll try to cover the paper, point out different things here. And after that, we'll try to cover its implementation in Pytorch. Let me move the Zoom things out of the way. And again, as a reminder to everybody in the call, please feel free to unmute and interrupt anytime. So this paper, as a reminder, came out in 2015, which is why you'll find some things that may or may not be true in today's date. It starts with, there is a large consent that successful training of deep networks required thousands, many thousands of annotated training samples. I should probably not try to underline things. Sorry about that. So the authors claim to present a network and strategy that relies on strong augmentation to be able to work more efficiently with samples. Now, this is another thing that I want to point out. Many times papers are quite regional to conferences. So for this paper, they were aiming for a particular challenge. And even though in the opening paragraph, they mention an emphasis on augmentations, we now have a lot more advanced augmentation, but still the architecture is the one I think is of key importance here. So the architecture in the intro, as the authors point out, consists of a contracting path. Think of this as your standard CNN. So in your head, just replace this with any ResNet, and we'll look at the architecture image in a second. The key thing after this, which I think this paper was the first to introduce, is the symmetric expanding path that enables precise localization. Now, this was much better than the sliding window convolution approach that was being used at the time, and there was another key reason to making the architecture work. And how I'll try to read the paper, I don't want to read every single line. I'll just be pointing out the key details. I've read this already for a group. And this is just to mention to everybody, if you'll be reading this paper later on, hopefully, please come back and ask any question that you want. So in the introduction, the authors point out two challenges. The first one is that the CNN approaches, the output is a single class label. But with biomedical images, it should include more localization. So more, I think, pixel level annotations. And the second one, which I've already pointed out, is the output size. Now, at that time, this paper had trained a network with a sliding window approach that somewhat worked with this, but it had two limitations. There were a lot of patches, and these were usually more than the number of images. So it was quite intensive, quite compute intensive to train this model. And it would require a lot of max pooling layers. So this older approach of using sliding windows, which I'm just glancing over here. So if you've not heard of it, you won't understand this. You can read the paper if you want, it's not necessary. But this paper required you to use a lot of max pooling layers. And generally when you do that, when you increase them a lot, the accuracy starts to decrease. So these were the drawbacks of the original paper that this architecture tries to overcome. And they do this by using a fully connected network and upsampling the output. So let's look at the architectural image. This is the classic unit architecture. The key thing to make it work, or there are a few key things, let me point out all of them. So think of this as an encoder. Think of this side as a decoder. So you have an encoder which shrinks the image size down. You have a decoder which increases the image size. It upsamples, performs the upconv operator to give it the output segmentation map. And thirdly, this was quite key to making things work. We also have a copy and crop, which copies over these feature maps over to the output. This, I believe, was introduced before ResNets in this paper, and this was also a key part of making ResNets work. So this is the copy and crop. This arrow represents that. So inside of this architecture, you start with the 572 by 572 image. you apply a 3x3 conv and a ReLU activation function on top of it, followed by which you apply a max pooling layer. You repeat this a bunch of times, and then you start the upconv or the up convolutional operator deconvolution, which resizes the image. And again, I want to point another key thing out. You don't get the exact same sizes as the input, but it gets quite close. So to recap, the key things introduced in this architecture was an encoder layer, a decoder layer. Inside of the encoder layer, if you just forget that there's even a decoder layer, this looks just like a fully connected, not a fully connected, sorry, a convolutional network, right? So think any ResNet or think AlexNet for that matter. You have a bunch of convolutions being applied, followed by max pooling, followed by a ReLU. Repeat this a bunch of times. You get a 1024 by, I think it's 28 by 28 output size. So this was already existent at that point. The key difference was having this deconvolution layers along with the copy and crop approach, which takes this feature maps, crops into it, and copies it across. Why do we crop into it? If you look closely, the sizes are slightly different, so you need to account for that. So what happens here is, let's say you have a human for some reason standing in this image. The authors just perform a center crop. So center crop is just cropping literally into the center of the image by leaving some pixels. Now you wouldn't have that in the middle of the convolutional neural network, but assume you have this image in this layer. You crop into it and copy it over to the output layer. This was one of the key things to making this work.
Sayyam, I had a question. Am I audible?
Please. Yes, you are. Please go for it.
I see that there are two convolutions applied simultaneously right in the very first input image, as in the original input size is 572 cross 572.
Mm-hmm.
And then the authors have applied two convolutional layers.
Mm-hmm.
I was going through the VGG paper, VGG 16 architecture, and there they had applied 3 convolutional layers. So is there any rule of thumb while applying convolutions in a CNN?
Now that you've mentioned it, I'm trying to think of it, no, I think it just depends on the architecture, and I assume it's also derived through just a lot of experimentation.
Yeah. So yeah, even I couldn't find this any rule of thumb while deciding the number of convolutions. I think it is just empirical evidence. I think so. It might perform.
I believe so.
Yeah.
Unless anyone else wants to chime in. Okay, that stays as a fact for now.
Thanks.
Yeah. I wanted to do side-by-side comparison, but not just to interrupt the flow. I'll probably come back to it. If you start thinking of this in code, right? At the end of the day, reading papers is exciting. You can try to go through them. After a while, you start getting the hang of the academic language, and it's really fulfilling to be able to understand a paper from end to end. But what you really should be doing, in my opinion, and what's really helped me, so it's my personal experience, please take it with a grain of salt. But whenever you're looking at a paper, start thinking of it in Pytorch. I use Pytorch, you could use Keras. Start thinking of what operators would replace the architecture. You can't always think of it, but it's a good idea to start building a mental image. So I'm thinking this could be con2D layers, right? Followed by a max pool layer. And this could become a block in itself. So let's say this is a block. We repeat this block a bunch of times, get the output. Now, so that becomes the encoder, right? Let's think how we could define the decoder. Let me actually write this down. So inside of the encoder block, as Devin pointed out, we have 2D, let's say, operators being applied, followed by a max pool, and maybe a ReLU as well after these. Sorry. And this is repeated, let's say, X number of times. So that is our encoder literally. You can call it as many times in the unit architecture. I have called it a bunch of times in different architectures. You can see the number changing. But in code, you could define it like so, right? This could be a function called encoder that has these layers. They could be in sequential, or as we'll see, you could put them in a module list. That becomes your encoder function. Let's think of the decoder function. So now this would be quite tricky to implement. And luckily we don't have to. I don't have to. I'm sure others in the call would be able to do it. But there is a deconv operator or a transpose conv operator in Pytorch. So decoder layer ideally would consist of them. So I'll skip writing that, but just to get a mental image, that's how it would look in code. And we'll look at the code in a bit. But this is the architecture to summarize real quickly. Let's continue reading in the paper and I'll try to cover any things. So further in the paper, the authors mentioned one more thing which I want to point out. One more important modification in our architecture is that in the upsampling part, so focus on the right part in your mental image. So in this decoder layer, in this upsampling path, we also have a large number of feature channels. So if you look at the numbers again, I'm sorry, I'm scrolling back and forth, but it's hard to cover both things. These numbers are really starting to increase. So these are the feature channels. They're quite large. That's what the authors are pointing out. And this is useful because it allows the network to propagate context information to higher resolution layers. So to answer your question from earlier, Sanjay, that's why this is important. If you just use padding, you don't have the contextual information. You could get away with having the same output sizes, but it won't be the same as having the feature channels because you lose out on the context. And that's why I'm sure it would be quite obvious by now, but that's why it's called unit, because it's a U-shaped architecture. I'll glance over the other details because in 2021, these aren't too important. You can get a much better GPU today on Colab than the authors had at their research labs. Today, research labs have even better GPUs. The authors also talk about data augmentation, which I'll mostly skip because we also have better approaches. I'll point out the approaches that you can use instead. I've already covered the network architecture, so scrolling past it. And again, as a reminder, I'm glancing over details just to cover as much breadth of knowledge. Happy to go into depth. Please interrupt anytime. The training in the paper is done with SCD. So the authors also prefer having smaller batch sizes to favor larger input tiles. So they prefer a large input size over a large batch size. Actually, they mentioned further they had a batch size of 1 because at the time they had a 6GB GPU. On Colab, you can try this exact same paper and have a much bigger batch size. They also mentioned that they used a high momentum value. If you don't know what that is, please ask. Otherwise, I'll skip. And further, they mentioned that using a weighted loss was also quite important. I should probably skip over the data augmentations, and I'll also skip over the experiments bit because since then a lot more papers have come out and we have different segmentation challenges, which I'll also point out. But to summarize, at that point in time, this architecture was quite different from the ones that existed it was really good in the fact that it first of all introduced this new approach of a unit architecture that actually worked. I've gone through the reference chain and noticed similar architecture at that point. But there were three things that helped it. So encoder decoder had been introduced earlier as well. But having this copy and crop approach, along with strong data augmentations, was really helpful in making this work. Skipping over more details, I think that's all I wanted to cover in the paper. So I've read through the paper, but not really, because I've just covered the key details, which is what is possible in a few minutes. I'll take a quick pause to see if there are any questions.
I have a quick question.
Please go for it.
So when they trained this architecture, they were using the input data as augmented or otherwise normal images, and the target data was segmented out labeled images, right? Okay. And we are saying that a convolutional set of layers and a deconvolutional set of layers are able to learn features that would be able to segment new images based on the features that they learn and blah, blah, blah. Right? That is what we are saying.
Correct. Oh. Assuming they're similar images. So like, let's say you're training on. Yep.
Right. So you mentioned that nowadays there are a lot of more other architectures that sort of do a better job. So again, I'm dumb. So what is the current state of the art in terms of image segmentation? Is it that Facebook's, what was it? Something on the other.
That's not a dumb question, Saurabh. That's a fantastic question. And I'm quite dumb as well because I don't know what that is. Even though I'm hosting the session. So let's check it out here. Let's say I want brain image segmentation. And this quickly brings up the best models corresponding with it. Or you can just head over to Papers with Code, browse the state of the art, head over to semantic segmentation and just find the best paper.
Will do. Thank you so much.
Sure thing.
Hi, just a quick question.
Please
compared to normal autoencoders like this seem to have this kind of crop and copy, something of that kind, right? Could you just give an intuitive explanation if I have any good understanding about it? Like,
intuitive explanation of, sorry?
As in like why from encoder they were cropping and copying it to the decoder parts, like.
Sure, I can go over that again. So I claimed, like, let's say in this second layer, which would never be the case, but let's say you have this image or this feature map lying inside of it, where you have this human. Now to give this context over to the output layer, because remember these are like much smaller numbers. We looked at the Excel sheet, which don't exactly correspond to it. And these are just learned numbers. Now to give the output some context of it, we crop into it because it's slightly smaller. So if you look at the numbers, if you zoom in enough, you can look at the numbers, you can glance over the details, but it's slightly so smaller. And for that reason, we'll crop into the image. So we'll crop into the green area of this image, which I'm claiming would probably be in the second layer. And we copy it over to the output and concatenate it there. Is that helpful?
All right.
Thanks for pointing the link out, Sahil. That's the file I'm using. File I was using for convolutions. And yep, Detectron is one of the. I think it's one of the best architectures, if not the best. Thanks, Yash. On segmentation, I might be wrong. Awesome. So further from here, I wanted to cover the implementation and I'm quite lazy and my colleague has already done it in his blog post. So I'll just steal his material from here, but to point it out, it's called a Pytorch implementation in 60 lines of code for unit. Also linked in this post, please find it there. And I've copied over the code from his article. Sorry, I'm just trying to rearrange my screen so that I can have these side by side. Let me bring this up to the left-hand side. Stop sharing. So what I'm trying to achieve here is just trying to share both the screens side by side. For some reason, Zoom won't allow that. Sorry, I'm quickly trying to arrange everything here. Let me try that now. Can everybody see both of these side by side? So the paper and the Jupyter notebook? Is the Jupyter notebook visible alongside the paper?
Yes.
Okay, thanks. So like I claimed earlier, we have this input, and I'm sorry it's not exactly overlapped. I could do a better job at it. Let me move this over a bit. As you can tell, it's quite live and I haven't practiced this thing exactly. But I want to point out the implementation by literally looking at the architecture on the side. So I'll keep focusing on left and right and speak it out as I do so. So the first thing we want to do is we want to implement a block. Now, what would the block for encoder include? And we're trying to implement the encoder first. So for that, we need to implement a block of operators that get repeated every time. Remember, whenever you're working on code, you just want to use or reuse anything, it's probably a good idea to define a function. So we're going to do that. Inside of the encoder, a blue arrow means a 3x3 convolution followed by a ReLU. And look closely, this is being done twice followed by a red arrow. What is a red arrow? It's a max pool of 2x2. So in the block, you of course have to call the init function, inside of which we can define the input channels, the output channels, and we'll call the super classes constructor. The kernel size will be 3. So inside of this, we define a conv 2D followed by a ReLU followed by another conv 2D. And the kernel size remains 3. So let's look at the function signature. The int channels defines. I just press shift tab twice for anyone that's not familiar with this. And what I was trying to achieve here is I wanted to point out what two different arguments do. So the in channels takes the number of channels in the input image. The out channels is the number of channels provided by the convolution. Kernel size, which is the third argument that we're passing, is size of the convolving kernel. So it's a 3x3 kernel in the original paper, which is what we're following here. So that's how we define our first conv layer, followed by ReLU, followed by conv2 layer. Inside of our forward function, remember the red arrow. Please look on the right-hand part of the screen. So we have two convs followed by a ReLU, right? First one, second one, and then ReLU. So the forward function inside of this block, so we're trying to repeat these blocks, which is why we're defining the function. The forward function returns ReLU applied on top of these. And this becomes a block inside of our encoder. From there, we can define our encoder class, which inherits from nn.module. And here we'll define all of these channels. These correspond to the input image sizes, so I'm not going to go over them. But from here, you'd like to define the encoder blocks. And we pass this into NN module list. What is a NN module list? You could press shift tab twice to get the details. Let's see. The docstring says it holds submodules in a list. The long story short version is it basically allows you to create a list of Pytorch functions to which you can append, extend, and perform all list-like functions. So encoder blocks will essentially have a list of modules of encoder. So all of the blocks inside of encoder. For that, we'll unpack all of the channels. So for I in range of all channels, remember Python is 0 indexed. So if we go from 0 to length of channels, we create a block and store it inside of an module list. What is block? We just defined it up above. So all of these operators get stored in encoder blocks. From there, you want to pass it to max pooling, which we haven't done so. Remember, I'm looking at the right-hand part of the screen. The red arrow is a max pool of 2 by 2. We're implementing the exact same thing. So we'll pass it to a max pool 2D with a 2 argument. Why is 2 an argument? Because the first argument is kernel size. This applies a 2D max pooling over an input signal. And the kernel size is the size of the window to take a max over. So we want to take a max over 2 by 2, which is why we pass max pool 2D of 2. Inside of the forward function, we create a list of FTRs. And we go over all of the blocks inside of encoder blocks. So we go over all of the function or all of the blocks. And we append this followed by a pooling layer and return this. So this defines our entire encoder block. Followed by which we'd like to define a decoder block as well. And if you pay close attention, you might see some correspondence from these numbers over here. These are the channels. Skip over it. And here we'll apply the conv transpose 2D function. Let's see what that is. Now I want to look at conv 2D, please. Transpose 2D. So let's look at the docstring. It applies a 2D transposed convolution operator over an input image composed of several input planes. That's what this function is going to do. And it can also compute the gradient, which is what we want. This takes the number of input channels, output channels, and kernel size. And we pass the list of channels here as an argument. So we define a upconv block where we pass this module list. And similarly for decoder blocks, we can create another module list where we pass blocks like so. I'm sorry, I'm having to scroll a bit, but it's quite hard to split my screen. I have a smaller monitor than I would like to. From there, we define the forward function for doing a forward pass. Now we're looking inside of the decoder, and here's how the forward function would look. So for the entire range of channels from 0 to length -1, because Python is 0 indexed, we take the upconv, and upconv just takes the conv transpose 2D. We store it in encoder FTRs. Now here's another thing. Remember this copy and crop. This was missing in our definition earlier in the constructor. So we crop the encoder features. We take the encoder features which are being passed here to this function. So in the forward pass, we take in the encoder features, which we crop into and call torchcat. What does torchcat do? Great question. Concatenates the given sequence of tensors in the given dimension. So we take these features, copy and crop, which is crop and cat. Now, this is what I mentioned earlier, like to go back a minute in time, when I said when you're looking at a paper, right? And ideally, the end goal for everyone joining us today is to not be required to join these, because you can do it by yourself. You're so good, which would hurt my role a bit, but that's what we want. So the next time you see copy and crop, right? Don't think copy and crop, think crop and cat. So always try to think of Pytorch functions in your head or Keras function. I'm not good at Keras, so I don't use it. Whenever you're looking at a paper, and that's how you'll start increasing your speed of trying to implement these. I haven't implemented this. Aman did, and I'm sure it took him a little while. And as you keep practicing this is what you should be focusing on. A little side note there, sorry about that. So this is how we've defined the forward function here, and we return this. Now we haven't defined crop, and this doesn't exist inside of Pytorch. So we define it here. It does exist inside of Torch Vision transforms. And from there, you can call center crop and you can return it. Later on inside of class unit, you can call all of these functions together. And I'm trying to see if there are any other details. No, there are not. You can just utilize all of these functions that you've created from earlier, and that becomes your architecture. So this complete image and this paper of 5 pages takes about 60 lines of code to implement. I also want to stop sharing my screen and share the right one again. Go full screen. So also to point out the official implementation, it's the first link here. It's slightly different to the approach we've taken here, but you can also go through it and understand it real quickly. So inside of this repository, if you head over to the unit folder, you can find the implementation and the functions defined right here. Slightly different, but not too different. I'm almost out of time, so I cannot cover them, but I just point everyone to this. So we have a few minutes and I'll try to take as many questions as I can.
Hey, Sanyam. I have a quick question about augmentations.
Sure.
So for augmentations, some typical augmentations would be rotation and like scale changes and such things. So I know segmentation is often used for OCR tech. And one of the like considerations for OCR is some characters look different when you rotate them. They resemble some other character. So how is that generally like how is that tackled when you're trying to do that?
That's a great question. I've worked a bit on this problem. And I did have my notes here, which I wasn't going through, but let's say you're trying to see what's in this notes on this paper. Ideally, you want to focus on this. I'm just going to derive the function. So the first thing you want to do is segment the paper out of this image, crop into that, right? Now let's say you've cropped into it. The text is somewhat readable, but not the most readable, right? So ideally, if I had the time, I'd walk over, switch off the light, which means I'll change the brightness so that it's more readable. Probably I'll adjust my camera a bit, let it focus, which means I've changed the contrast. So the augmentations become cropping in, changing the brightness, changing the contrast.
Right. So yeah, those are the first like things that you would do if you were doing an OCR. But other augmentations, to make it more robust, you typically would rotate an image, right? Or rotate you would rotate an image to make it invariant to certain transformations.
For OCR, maybe just to a few degrees, but not like completely by 90 degrees.
Okay. All right. Thanks.
Sure. I'll probably also point out, so I hosted the Pytorch reading group for a bit, and there we looked at augmentations in depth. But if you head over to the Weights and Biases channel, you should be able to find a albumentations walkthrough in one of the lectures. So if you go to our channel and check out, I'm not going to open my YouTube because you all will see my recommendations. But if you find the Pytorch playlist, you can find a walkthrough of albumentations where I do discuss this in depth and I cover OCR there. But I would really trust this library a lot. It's implemented by one of the best Kaggle grandmasters and really leaders of research. And people who are in the industry who really have thought a lot about this. Great question, Ramesh. I have to mention this as well. I don't understand why Ramesh joins my study groups, because he doesn't need to learn about these things. Rather, he should be teaching them. So I'll probably invite him at some point. One of the suggested homework is, all of these suggested homework is Kaggle competitions. So the official implementation actually walks you through how to take this and apply units to Caravana competition. All of these are Kaggle competitions, by the way. The other blog I referred to shows you how to implement it on TGS competition. Another one is on Pneumonthrax competition. And I want everyone to go to these competitions, apply unit without cheating, without looking at what we discussed, and try to get into the top 30%. For that, you'll need a few things, and you'll also probably have to use albumentations. So great question for OCR. Luckily, we don't have to worry about working with text, but we should look at image augmentation. So I'll leave you all with the homework to check out albumentations. Take the unit architecture and try to apply it on one or all of these competitions, and please consider writing about it. I can go on for hours talking about how blogging about things has changed my career in machine learning, but if you write about anything you learn, in my opinion, it really solidifies your learning. So that's suggested homework. Thanks for asking that. All right, we're 1 minute overboard, but I'll take one last question, if any. Awesome. Thanks everyone for joining. I hope this was helpful to everybody. Please feel free to leave a reply for any papers you want me to cover. We'll be meeting at least once a month to go through papers. My goal is to teach the key concept in a classical paper, if it's a classical paper, and cover the implementation. If it's a recent paper, I'll try to cover them in more depth. Thank you so much for joining on a Sunday morning, afternoon, or evening, and I look forward to seeing you in the other community events.